So this is a review for exam 2, which is over limits and derivatives. So we're going to start here in number 1, and we're going to use the graph below of the function f of x to answer the following questions. And so the first thing we want to figure out is, where is this function not continuous? And we're going to state this in terms of the x values. And so the idea is that you can trace this function without lifting your pen or pencil. It's all the way, it's fine here, and it goes down, and it's fine. This is the first sort of spot where you have to jump, and so where you jump, you're not continuous anymore, so this is x equals 0. And then you pick it back up, and you're continuous, but then you have to jump up to this darkened circle, and then jump down, so also x equal to 2. So 0, and we'll put 2 there, and then you're continuous the rest of the way. And then in the second part, we want to figure out, where is the function not differentiable. So remember, differentiability means smoothness. So you're smooth. Right here, there's a sharp point. So it's where you can kind of hurt yourself if you touch the function. So x equal to -1. And then you're smooth, and now this is a sharp point right here, because if you put your hand on it, it'd stab your hand. Up here and down here, so x equal 0. And then you're smooth, and right here you get a splinter if you ran your hand over it, so also x equal to 2. So there's 3 points where the function is not differentiable. Alright, so the next problem we're going to look at is where the function, we're going to do limits. So here are my limits, and we want to determine the following limits here. So let's look at this first one. So the first one says, what happens as x goes to 0 from the right? So it says plus, which means coming from the right. So over here, here's x equals 0. And if you come in from the right-hand side, you're going to follow this function down to -1. So this answer is equal to -1. Whereas in part B, you're going to come in from the left-hand side. So if I come in from the left-hand side is 0, so here's the left is 0, you're going to approach height 0. So this answer is equal to 0. And then finally, in part C, it says what happens to the value of the function as x approaches 0. So find the limit as x goes to 0 of f of x. And this is going to equal d in e, which means does not exist, because the limit from the right is -1 and the limit from the left is 0. And since those values are not the same, we conclude that the limit does not exist. And so then in part D, we look as the limit goes to -2. And so here's -2 over here. And as we come in from, let's do the right-hand side, that's -2. And as we come in from the left-hand side, it's 0. Right. And as we come in from the left-hand side, the height is 0. So it has the same left-hand and right-hand limit, so the answer is 0. For part E, we're looking as x goes to -infinity. So what happens to the function as you look to the left? So as you go left, it keeps going up, but it approaches this height of 2, because it's a horizontal axis. So this answer is equal to 2. And the next limit over here, as we go to 2, let's see what happens. So the limit as x approaches 2 of f of x, so here's 2 right here. As you come in from the left-hand side, it's going to be equal to height 1. And as you come in from the right-hand side, it's going to equal height 1. So this is equal to 1, even though the actual value is height 2. Remember, the limit does not care what happens at 2, it just cares about what happens around x equal 2. And now we're going to look and see what happens to the function as you go further to the right. So as you go to the right, this function continues to go down, and it goes down forever. So we'll write equals -infinity to indicate it's going to go down forever. And then as x goes to -4, so here's -4 over here. From the left, it's going to approach 0, and from the right, it's going to approach 0. So the answer to this limit is 0. And then finally, as x goes to -1, let's change colors. So as x goes to -1, what will happen to the height of the function? So as you go to -1, From the right-hand side, you approach height 1. From the left-hand side, you approach height 1, so the answer must be equal to 1. So that's the idea. Let's get rid of all these drawings here so we can start talking about number 4. So in number 4, what we want to do is we want to determine the sign of f, f prime, and f double prime from the graph. All right, so let's start here. So this says, what is f of -4? So I look at -4, and the height is 0. So this is 0. And then f prime of -5, so here is -5. And that means I'm up here on my graph. And this is going what? Down. All right, so it's going down, so it's decreasing. So the derivative must be, hopefully you think, negative, because the derivative, I say derivative, you say rate of change. So if the function is decreasing, which it is, you always read left to right, so it's going down, so it must be negative. We can even do this one down here, since it says f double prime of -5. So here, this is part of a frown, all right, so it's concave down. That means the second derivative is negative, because the second derivative tells us about concavity. And then over here at f of -4, so let's change colors. So let's do this one, f prime of -4. So here's -4, and I'm right here on my graph, and I'm decreasing. So f prime is going to be negative. And then let's do this one, f prime of -3. So here's -3. And so I'm right here on my graph. And this is f double prime, and this is part of a smile, so it's concave up. So the second derivative is positive. And then finally, f prime of 1. So here's 1. And I'm up here on this part of my graph. And so f prime of 1, since it's going up, it's increasing, the derivative will be positive. So remember the saying, positive ideas go with positive quantities, negative ideas go with negative quantities. The first derivative tells us about increasing versus decreasing. The second derivative tells us about concave up versus concave down. If the first derivative is positive, it's going to be the positive idea of increasing. Whereas if the first derivative is negative, it's going to be the negative idea of decreasing. If the second derivative is positive, it's going to be the positive idea of concave up. Whereas if the second derivative is negative, it's going to be the negative idea of concave down. And vice versa. It goes both ways. The next problem we want to look at is a series of limits. And so we're going to start here with part A. And so we're going to take the limit as x goes to 5 of pi x plus cosine of x. And so the idea of working with a limit when you're using a formula is just to first plug in the points. So let's plug in 5. So I have pi times 5 plus cosine of 5, which is equal to, I'd probably write this as 5 pi plus cosine of 5. And that's just some number. And so although it may seem strange to you, the limit says that's the answer. If you plug the number in and you get out an answer that's reasonable, that's your answer. The next one we're going to do, part B, we're going to take the limit as x goes to -1 of x plus 1 over x squared minus 5x minus 6. And the first idea is to simply plug in the limit. So plug in -1, and I'm going to get -1 plus 1 on top, and then I'm going to get -1 squared minus a 5 times a -1 minus 6. And you can already tell on top you're going to have 0, and you can guess on bottom you should also get 0, because this is a certain type of problem which leads to an indeterminate form, which simply means that the limit cannot be determined in the given form. So you're going to have to do more work. So over here, what I'm going to do is I'm going to rewrite this as the limit as x goes to -1. I have x plus 1 on top, and I'm going to factor the bottom. So I'm going to have this as, what, x minus 6 times x plus 1. And when I do this, what's going to happen is that this x plus 1 is going to cancel on top and bottom, and that's my indeterminate form basically going away. And so this is going to equal the limit as x goes to -1 of 1 over x minus 6. And now I'll plug in -1 for x, so I can drop off the limit. You drop off the limit when you evaluate it, which means plug in x equal -1, so -1 minus 6, and I get 1 over -7, so minus 1/7 for my answer. On part C, let's see what we have. So we have the limit as x goes to 7 of x cubed minus 8x squared plus 7, all divided by x minus 7. And so what I'm going to do is I'm going to plug in 7, and so I'll have 7 cubed on top minus 8 times 7 squared plus 7, all divided by 7 minus 7. And so let's see, what number do I get on top? I'll probably use my, well, I actually don't have to use my calculator. Right, my brain's ticking away here, and my brain's saying 8 is 1 plus 7. So this is really 1 plus 7 times 7 squared plus 7, all divided by 7 minus 7, which is 0. So now I know I'm going to be in trouble here, so I'm going to start putting quotes around this. And then my brain automatically says that on top here, what do I have? Well, I have 7 cubed minus 7 squared plus 7 cubed. So minus, I can multiply through by the 7 plus 7 cubed. And this is all in parentheses. And then plus another 7 all over 0 on the bottom. And I see now that these 7 cubes are going to cancel. And you may say it's faster to use a calculator. And I say it's probably better to use your brain in the end. And so 7 cubes are going to cancel. And so I'm going to get this to be equal to minus 49 plus 7 all over 0, which is equal to negative 42 over 0, which you may not think is a nice number, but the idea is that there's a nice number on top and there's a really small number on the bottom, not quite 0. That's why I put it in quotes. I'm kind of thinking. And so this is going to be equal to plus or minus infinity, basically. So this limit's we're going to say it does not exist. It's not an indeterminate form. It's not a 0 over 0. It's some positive or negative number, in this case negative 42, number close to negative 42, divided by some really, really small number close to 0. And so it's going to either blow up and blow down. So the limit does not exist. Part D, let's take a look at it. What do we have? We have the limit as x goes to 1 of sine of x minus 1, all divided by x minus 1. And so again, the idea is you always plug in the limit. You evaluate the limit to see what happens. So I drop off the limit sign because I'm going to plug in 1. And I'm going to get sine of 0 divided by 0, which is equal to 0 over 0, which again is this indeterminate form. So I simply cannot determine a limit in its given form, so I'll have to do some more work here. And the more work I'm going to do is I basically have no idea how to work with this algebraically, but I do understand the concept of a limit. A limit basically poses the question, when I write this down, it's asking, or it's saying, hey, as x gets closer and closer to 1, what does this thing approach? And so what I can do is plug in a number for x that's close to 1, like 1.001. And then I can plug it into my function. So on this side, I'll test it on x sine of x minus 1 divided by x minus 1. And so I'll do sine of 1.001 minus 1, all divided by 1.001 minus 1. And I'll need to use my calculator to do this. So here's my calculator, and you should make sure that you're in radians. So if you are not in radians, hit mode and go down to radians and click on it. And so then I can do sine of 1.001 minus 1 divided by, and I'll do left parenthesis 1.001 minus 1. And I get out a number, 0.9999, and so on. And I can even do this. This is from the right of 1. I can even do it from the left of 1. So I put in let's just do 0.999. And so I can do the same thing to see if I get a similar limit from both sides. So 0.999. So this is a number to the left of 1, 0.999. And I get out this same sort of number, 0.9999, blah, blah, blah. And so this was basically the same thing, right? So the sine of 0.999 minus 1, all divided by 0.999 minus 1. And so my guess then, this implies, if I had to make a stab at what the limit as x approaches 1 of sine of x minus 1 over x minus 1 was equal to, I'd say, hey, I bet it's equal to 1, because these numbers are really close to the nice number of 1. So that's my answer. So when in doubt, you can always make a table, as long as you can identify the number that's being, the limit that's being expressed here in some sense, what number these are approaching. Let's take a look at part E. So on E, what do we have? So I have the limit as x goes to infinity this time. So these are limits going to infinity of 2 plus x squared minus 14 x cubed, and then plus 5x. And then on the bottom, I have x plus x cubed. And so when you're working with limits at infinity, the idea is that basically there's going to be some term on top that's going to dominate, and there's going to be some term on bottom that's going to dominate. And for polynomials, it's always the highest degree term. So the highest degree term is this negative 14x cubed. So you can basically just cross off these lower degree terms because the idea is this is such a big number. When you cube it, these numbers don't matter anymore. It's sort of like you have $1 billion compared to 10 cents. You know, it doesn't really matter if you have $1 billion or $1 billion and 10 cents. The 10 cents is trivial, so you can cross off the trivial expressions. Down here, the x cubed will dominate. The highest power is x cubed, so it'll dominate, so you can cross off this. So this is really equal to the limit as x goes to infinity of negative 14 x cubed over x cubed, because these terms are going to be the ones that dominate. And then again, things are going to cancel, so this x cubed is going to cancel with this x cubed on the bottom. So this is going to be the limit as x goes to infinity of negative 14. And so that's going to be equal to a negative 14 is my answer. And then the last limit on this page, this was the limit as you go to negative infinity, which in this case it didn't matter. If you went to positive or negative, it's still going to go to negative 14 either way, but that is a negative infinity. And then on part F, we have a limit as x goes to positive infinity, and then this is 2 minus 3 to the 2x. divided by, oops, there's an e there. Let's fix that. So I have the positive infinity, and I have 2 minus 3 e to the 2x. Now I got it. All divided by x minus 7 e to the 3x. And so if you plug in infinity, you'll see you're going to get this infinity over infinity form out. So this is also an indeterminate form we'll talk about later. But when you have infinity over infinity, it's also called an indeterminate form because you can't determine the limit as given. The idea is sometimes the top is going faster to infinity than the bottom. Sometimes the bottom's going faster to infinity than the top. And sometimes they're going to infinity at the same rate. That's how you get out this number like negative 14. So what you want to do here is you have to realize that certain terms are going to dominate, and it's really this exponential terms that are going to dominate. So this term won't matter, and this term won't matter. And so this is going to be equal to the limit as x goes to infinity of negative 3 e to the 2x divided by negative 7 e to the 3x. And here's where you have to be careful. You can actually cancel off things here. Exponents, if you want, they can subtract. So this is actually equal to then, let's make a barrier over here, and let's extend the page. And so this is going to be equal to the limit as x goes to infinity of what? So you're going to have a negative 3 on top, but on bottom you're going to get a negative 7 e to the x. There are a couple of ways to see this. If you want e to the 3x, you could write this as e to the 2x times e to the x, because exponents add. Then you see obviously the e to the 2x's will cancel, and you'll be left with an e to the x in the bottom. And so then this is equal to, when you plug in infinity, you're going to get negative 3 divided by negative 7 e to the infinity, which is you have some number on top and you have a huge number in the bottom. I mean, it's enormous. Just do like e to the 10th on your calculator. And so this is going to be like 0. So some number divided by a huge number you cannot ever possibly imagine is like 0. Now, if you change this problem and you do the limit as x goes to infinity, and we're switching it up now, of 2 minus 3 e to the 3x divided by x minus 7 e to the 3x, you can see now that something else is going to happen. So now when you do the simplification, these e to 3x's will cancel, and you'll actually get 3/7 out. So that's another type of problem that I could ask on the exam. All right, number 3. So number 3 says consider the following function. So we have a piecewise defined function. And so f of x is equal to cosine of x if x is less than or equal to negative 2, and sine x minus 2 if x is greater than negative 2. And then in part A, what we want to do is use left hand and right hand limits to determine what this limit might be. So we're trying to figure out what is the limit as x goes to negative 2 of f of x. Now cosine of x and sine x minus 2, these are nice and continuous functions, so the only thing we have to worry about is what basically happens here at negative 2. Do they match up? Do they not match up? If they don't match up, this limit will not exist. If they do match up, then the limit will exist. So we want to look at the limit as x goes to negative 2 from the left, and so that's of f of x. And then from the left-hand side, so let's draw a picture down here. So think about this. So here's my picture. Here's negative 2. If you're coming in from the left-hand side, you're less than. Let's color code it. So I'm coming in from the left-hand side of negative 2. So I use this piece. And so this is going to be equal to the limit as x goes to 2. And you can keep it from the left if you want, of cosine x. And so that's just equal to cosine of 2. And so there's my answer from the left-hand side. And then from the right-hand side, I'm going to do the same sort of thing. I have the limit as x goes to 2 from the right-hand side of f of x. And so this is going to equal, now in this case, I'm approaching from the right-hand side, so I'm coming in from this way. And so those are numbers that are bigger than negative 2, so I'm going to use this piece of the function. So this is going to be the limit as x goes to 2 from the right-hand side of f of x, which is going to equal, oops, why don't I just plug in the limit there, right? So the actual function, sine of x minus 2, and that's going to equal, plug in a number, sine of 2 minus 2, and that's a plus there. And when I hit back, it deleted it. And so I get sine of 2 minus 2. Now, I don't know what these numbers are, but I'm pretty sure they're not the same, but if you really want to, you can check it. So on your calculator, you can take cosine of 2 and hit enter, and you certainly can take sine of 2 minus 2 and hit enter, and you certainly do not get out the same answer. That number is not equal to that number. So what I'm going to conclude here is that this limit does not exist. And then part B says use the definition of continuity to explain why this function is or is not continuous at x equal to negative 2. Now there are all sorts of ways to determine whether this function is continuous. You can graph it on your calculator, and you'll see that it's not continuous at 2. And the reason it's not continuous at 2 is because if you approach negative 2 from the left, you hit this height. If you approach negative 2 from the right, you hit that height, and they're not the same. So what you have is a sort of jump at negative 2. But I can explain it with the definition. So remember, a function, f of x, is continuous at some point x equal a if you take the limit as x approaches a of the function. And so this is sort of like your best guess by looking at values around a, if that's equal to the actual value, if that's equal to f of a. And so that's really the definition of continuity at a point. And so what we can say is that, well, the limit as x approaches negative 2 of f of x, well, we already concluded that this does not exist. Right, it did not exist because these two numbers here were different. So the limit from the left and limit from the right don't agree. So it's not equal to the actual value f of negative 2. And you can even figure out f of negative 2 by looking at the original function. If x is negative 2, then you use cosine of x. And so this is a cosine of negative 2. Oh, and I have to fix my solution a little bit. So you probably noticed this right here. For some reason, I dropped off a negative sign. So this should be as you go to negative 2 from the left. And so that's cosine of negative 2. So let's put parentheses around that. And then down here, the same thing. I don't know what happened, but I dropped off my negative signs. But I'm going to fix it right now. So that's negative 2. And so then this is sine of negative 2. And so I guess, of course, I should come back here and prove to you that these values are still not equal. So negative 2. And then sine of negative 2 minus 2. So yes, they're still not equal. All right. So my final conclusion here is because this definition is not satisfied, so this limit does not exist, so it's not equal to the actual value. Therefore, f is not continuous at x equal negative 2. So on number 4, we're given this function f of x equals 1 over 4x, and we have various parts we want to answer. So on part A, it says use the average rate of change to estimate f prime of 5. So the idea behind this is that if we want to find f prime of 5, we can approximate this by taking f of some value close to 5. So let's do like f 5 point, oh, I don't know. Let's do 001, and then take away f of 5 and divide by 5.001 minus 5. So this is the idea of average rate of change. And remember, this average rate of change, it's just this sort of formalization of the change in the output over the change in the input. And so we take the change in the output here, divide by the change of the input. And so this is simply, wherever I see an x, I plug in 5.001. So this would be 4 times 5.001 minus 1 over 4 times 5. And then this would be divided by 0.001. And I'm going to need a calculator to do this. So I have 1 left parenthesis, 1 divided by left parenthesis 4 times 5.001 in parenthesis, and then minus 1 divided by 4 times 5 is 20, so I'll just do 1 divided by 20 in parenthesis divided by 0.001. And I should get out a nice number, which it looks like negative 0.01. So let's just write this down. So this is going to be negative 0.0099. What else do I have here? 98, blah, blah, blah. And so I would guess that this is about negative 0.01 would be my answer, because that's what it looks like it's close to. Now in part B, we want to actually use the definition of the derivative. So let's do that. So part B, I want to find f prime of x. And so that's the limit as h goes to 0 of what? F of x plus h minus f of x, all divided by h. And so this is then equal to the limit as h goes to 0. And I have to figure out what f of x plus h is. So here's my x plus h. Remember, I'm just going to plug that in for my x. So wherever I see an x, I'm going to plug in an x plus h. And so what I'm going to have here is 1 over 4 times x plus h minus my f of x, which is 1 over 4x, and of course all divided by h. And so this is going to be equal to then, I need to find a common denominator. So the way that I'm going to do this is I just bring them together. I have a 4 and I have a 4, so that's good. I have an x here, so I want to put an x here. So if I put an x down there, I better put it up here. So it's the same fraction. And now I have an x plus h over here, so I want one over here too. So I have a common denominator now, and if I put it down there, I better put it up here. Otherwise, I won't have the same fraction as I did before. And so now I can bring these two fractions together because I have a common denominator. So this is going to be the limit as h goes to 0 of x minus the quantity x plus h, all divided by 4x times x plus h. And then that's all divided by h, which is this is equal to then, nice and slow, one step at a time, I have x, and I'll distribute that minus sign through, so minus x and minus h, all divided by 4x times x plus h, and then that's all divided by h. And so I see now the reason why I found a common denominator is because I knew something would cancel, and so these x's cancel, and I'm left with this being equal to the limit as h goes to 0. And then I have a negative h on top, a 4x, and x plus h on the bottom. And then that's all divided by h. And so on top, my algebra is basically done. And so what I need to do now is I have to realize I'm actually dividing by a fraction. So to simplify this, I can multiply by the reciprocal of h over 1. Which is 1 over h. And then my h's will cancel. So cancel, cancel. And then this is equal to the limit as h goes to 0, negative 1 over 4x, then times x plus h. I'm going to evaluate the limit now, so I drop off the limit, so I have negative 1, 4x times x plus 0. Notice I plug in 0 for h, not x, because h is approaching 0. And then this is just equal to negative 1 over 4, and then x times x is x squared. So that's my answer. So my derivative is negative 1 over 4x squared. In part C, we want to use the definition of the derivative again to find f double prime of x. So f double prime of x is equal to, and I write down the definition, the limit as h goes to 0 of f prime of x plus h minus f prime of x all divided by h. And I simply do what it says. But now I'm going to use this for my function because it's the derivative. And so I have the limit as h goes to 0 of negative 1 over 4. And now remember, I have f prime of x plus h, so wherever I see an x, I'm going to replace it with an x plus h. So I have x plus h quantity squared, and then minus a negative 1 over 4x squared, because I take off f prime of x, and then that's all divided by h. All right, so now I want to get a common denominator. So I have 4's, but I want an x squared. So again, I just put an x squared here. And if I put an x squared there, I better put it on top. And over here, I'll put an x plus h quantity squared on bottom, and I better put it on top, otherwise I'll change that fraction. And I realize a negative negative turns this into a positive. And so this is going to equal the limit as h goes to 0 of negative x squared. Now that I have my common denominator, then it's going to be plus x plus h quantity squared, all divided by a 4x squared x plus h quantity squared. And then this is all divided by h. And so that's going to equal the limit as h goes to 0. Now I want to multiply out x plus h squared, so I'm going to have a minus x squared plus x plus h times x plus h. I have x squared plus the middle term, 2xh, plus h squared. And then this is going to be divided by this 4x squared at an x plus h quantity squared, and all divided by h. And the reason why I found a common denominator and multiplied that out is because I knew things would cancel. So that cancels, and that with that. And then I can rewrite this as the limit as h goes to 0 of 2xh plus h squared, all divided by 4x squared, x plus h quantity squared. And that's all divided by h. So on top, the basic algebra is done. What I'm left with then is to realize I'm dividing by a fraction, h over 1. So it's like multiplying by the reciprocal . 1 over h. And if you allow me here, you're going to see h's are going to cancel, and the way that they're going to cancel is that I can actually move out a single h here. So I can factor out an h out of this top part, so h here and h here, so then I have a 2x plus h there, and so these h's then cancel off. And I'm left with this being equal to the limit as h goes to 0 of 2x plus h divided by 4x squared quantity x plus h squared. And hopefully the indeterminate form went away when I crossed off those h's, and it did. So if I plug in 0 now, I evaluate the limit, so I drop off the limit sign. So I have 2x plus 0 over 4x squared, all times x plus 0, quantity squared, which is equal to, I have a 2x on top, and then I have a 4x squared times x squared on the bottom, which again continues to cancel. So I have 2x over 4x to the fourth, which continues to cancel to 1 over 2x cubed. And so there's my second derivative. So there's one last problem for this number 4. And so the last problem is this part D. And on part D, I want to find the equation of the tangent line. So find equation of the tangent line at x equal 5. So let's make sure we understand what this problem is actually asking. The graph of the function, so they give you this function f of x, is equal to 1 over 4x. And you can graph this if you want. I'll tell you what it's going to look like. On the right-hand side, it's going to look something like this. And on the left-hand side, it's going to look something like that. And at x equals 5, so if you go and find x equals 5, here's 5, you'll find out that this is 5, comma, and then, of course, f of 5, the output, is equal to 1 over 4 times 5, which is equal to 1/20th. So my output is 1/20th. And at this point, there's a tangent line. And so we can draw or sketch the tangent line if you want. So there's my tangent line. I have a point right here. And to find the equation of a line, I know it's given by y minus y1 equals m times x minus x sub 1. So I have a point. All I need is the m, which we call the slope. The slope is the rate of change. I say rate of change, you say derivative. So what we need to find is f prime of 5. And there's two ways to do this. In part A, if you go back up here, in part A, you found f prime of 5 to be negative 0.01. Or you could simply use the fact that the derivative is negative 1 over 4x squared. So we could use, if you like, the fact that we found f prime of x is equal to negative 1 over 4x squared. So this should equal negative 1 over 4 times 5 squared, which is equal to negative 1 over 100, which again is negative 0.01. And now what we can do is, since I have point and I have my slope, I can plug it in to point slope form and find my answer. So y minus 1 over 20 is going to equal negative 1 over 100, and then times x minus 5. And so we solve this equation. So y minus 1 over 20 is equal to negative 1 over 100 times x. And then negative 1 over 100 times negative 5 is positive 5 over 100. And then we add 1 over 20 to both sides. So y is going to equal negative 1 over 100 x plus 5 over 100 is actually also 1/20th. And we add another 1/20th because we're adding to both sides. And so we get our answer to be equal y equals negative 1 over 100 x plus 2 over 20. So 2 over 20 is 1/10. So you could write it like that, or if you like decimals, you could write this as y equals negative 0.01 x plus 0.10. Doesn't matter. Either way works for me. So moving on to number 5, what do we have? So on this one, it says the temperature T in degrees Celsius of a hot cup of coffee just poured from the coffee pot is given by T of T, where T is the minutes since the coffee was poured. So you have this function capital T. They chose capital T because it describes the temperature, and it depends upon little t, which is the minutes since the coffee was poured. And so you know the idea. Coffee coming out of the coffee pot is hot, and after it's poured, it cools to room temperature. And the first question is asking, what are the units of T prime of T? Of T prime of 10. Now the 10 really doesn't matter. They could have just said, what are the units of T prime of T? The 10 is basically what's happening after 10 minutes here. But remember, T prime of T you could write as dt, right, D capital T, D little t. Same different notation, same meaning. And so the units of this thing are going to be degrees Celsius. So degrees Celsius per, and on bottom we have time, which is you can see up here in minutes. So per minute. So that's the degrees, which makes sense. It tells us how the coffee is cooling in some sense, the rate of change, the temperature of the coffee, right? Because I say derivative, you say rate of change. And so the rate of change of the temperature of the coffee is in degrees Celsius per minute here. Okay, part B, is T prime of T positive or negative, and why? So hopefully I say derivative, you say rate of change, because we know the rate of change of the temperature is negative because it's not heating up after you pour it into your coffee cup, it's cooling down. So remember, this derivative is the same thing as the rate of change. And so when I think of this T prime of T, I think, oh, this is the rate of change of the temperature. This is the rate of change of the temp with respect to time. And because it's cooling, I know my answer here. Because it's cooling, T prime of T is going to be negative. So I'm going to put negative here. And this is because the cup of coffee is cooling. Right? Or you could say the temperature is decreasing, which is just a fancy way to say that the coffee is cooling. All right, so the temperature is decreasing. And then in part C, we want to answer the question, but not for T prime, but T double prime. So what are the units of T double prime of 10? Again, the 10 really isn't that important. The 10 stands for after 10 minutes. But if I want to figure out the units of T double prime of little t, and you can put a 10 there if you want. One way to do this is to think of how you would write this in the D notation. So the D notation would be D squared capital T dt squared. And the way you find this is you take the derivative of dt. So the derivative of the temperature, take the derivative of the temperature with respect to time with respect to time. So that's a mouthful, right? The derivative of the temperature with respect to time with respect to time. But here the units then become real simple. So dt over little dt, right here you have degrees Celsius per minute on top. And then on the bottom, you also have this then per minute. Let's put it like this, per minute. And that kind of makes sense. The second derivative is the rate of change of the first derivative. So up here are the units of the first derivative, and down here is the gives us the rate, right, the minutes part. You could also write this if you don't like it written like that. You can write it more like we would write acceleration. So degrees Celsius per minute squared. You could also write it like that. And then in part D, is D double prime of T positive or negative, and why? So remember, this is basically concave up or concave down. Let's do this one right here. So to do this, There's several ways to do it, but I think really the best way to do it is just to try to draw a picture, because you should be able to kind of graph what this temperature is doing. So down here I have 0, and this is little t for the time, and here's the actual temperature. So when you pour a cup of coffee, I have no idea how hot a cup of coffee is, but I know it's up here. So I know it starts, let's say, up here. And then after a while, let's put just room temperature down here. So room temp. After a while, it's going to cool towards room temp. And the way that it cools, I understand. And there's basically 3 pictures you can give. You can give this picture where it cools like this over time. You could give me this picture. Oops, let's change the color. Over time. Or you could give me this last picture. Looks something like this over time. All right, so which graph is it? Is it the green, the black, or the red? And I'll tell you, I color-coded them for a reason, because the good one is always the green. All right. The red one basically says in the beginning it cools real slowly, then it starts to cool off real fast. The black one says it cools at the same rate all the time, and the green one says it cools off kind of fast in the beginning, but then it starts to slow down in the end as it starts to cool towards room temperature. So if you know about anything when you bake it, in the beginning it starts to cool off real fast, and then it starts to cool off slower and slower and slower. And so from the picture, I could say that this is going to be, since it's concave up, it's part of a smile, I know it's going to be positive. Right, so I'd say, okay, this is going to be positive. And if I was going to put this in, layman's terms, I'd say, oh, because the cup of coffee is cooling quickly, in the beginning, after it's poured, let's say. So it's cooling quickly after it's poured. After it's poured. After it is poured. And slower later, let's say. So that's how I might explain. Hey, in the beginning, my temperature is going down quickly in the beginning, but then it sort of levels off and heads towards room temperature. More precisely, like we did down here, the temperature is decreasing. We could say the temperature, the rate of change, and this is where you have to be kind of careful. The rate of change of the temperature is actually increasing because it's more negative over here. The rate of change of the temperature is increasing. So let's move on to number 6. So in number 6, what do we want to do? We want to draw a graph for each of the properties below. Okay, so in part A, you have the second derivative positive when x is greater than 1, the second derivative negative when x is less than 1. You have f prime of 1 to be undefined, which means it's not differentiable at x equal 1, and f is not continuous at x equal to 1. So let's sort of decipher this a little bit. So f del prime greater than 0 for x bigger than 1. What does that mean? That means it's concave up for x bigger than 1. So if I'm going to make a graph of this, I'll draw my x and my y-axis. It looks like I have a problem here at 1. So I'll put 1 right here. And I know that when x is bigger than 1, this graph needs to be concave up. So I'm going to write CU over here. I know I'm going to be concave up on this side. Whereas it's less than 0 when x is less than 1. So I know that the second derivative, when it's less than 0, when it's negative, it's concave down. So it's going to be concave down to the left of 1, so over here. F prime of 1 is undefined. So here it means it's not differentiable, so I'm going to have a problem here. I could have a sharp corner. That's one possibility. I could also have an asymptote there too. Or I could even have a jump. So you could have an. Let me finish that. So I could have this asymptote, or I could even have a jump. Those would all be 3 things that make f prime of 1 undefined, and it's not continuous there. Okay, so if it's not continuous there, what that tells me is that basically I'm not going to have a sharp corner, because at a sharp corner I'm continuous. So I can either have an asymptote or a jump. And you can pick which one you like. Maybe I want to have a jump there. So what I'll do at 1 is I'll make a jump so that I'm concave up over here. So I need to be concave up over here. So there's concave up on this side. And then I'll make a jump. Oh, who cares? I don't know where it's going to be. Oh, let's put it down here. So there's a open hole here, and I certainly can make it concave down on this side, like that. Perfect. So that satisfies the conditions. I'm concave up over here. I'm concave down over there. F prime of 1 is not defined because there's a jump here, so there's no derivative, and it's not continuous there. And part B, one thing changes. So on part B, this is the same, this is the same, this is the same, but now I want to make it continuous at x equal 1. And so if I want to make it continuous, I'm thinking I'll probably bring back this sharp corner option, because that'll make it continuous there. So on part B, let's redo this picture a little bit. So I have my y and my x-axis. And then I'm going to have this point 1. And again, I need to be concave up over here and concave down over here. And I want to be continuous at x equals 1. So on this time, I'm going to try to do this. Let's start with this point right here. It's got to be continuous, so it's easy to be concave up. Here's concave up. And then over here, I need to make a sharp corner. So to be concave down, I'm just going to start jetting out right here. And that needs to be a sharp corner. That looks pretty sharp. It looks like if I smacked my hand against it or hit my head on it, it would definitely hurt. So it is concave down on this side. It's concave up on this side. It's continuous because I can draw it without lifting my pen here. But the derivative doesn't exist because from this way it has one rate of change, but from this way it has a completely different rate of change. And that's what gives us this sharp corner here. And then finally, number 7, the last problem, we want to explain the 3 value theorems and draw a picture illustrating each one. So we have 3 value theorems: the intermediate value theorem, the mean value theorem, and the extreme value theorem. And I'm going to put the intermediate and extreme together because they only depend upon one thing, really. They depend upon the fact that the assumption that f is continuous, and that's basically it. So f is continuous on this closed interval a and b. So the assumption is valid in all 3, but that's all you need for the intermediate value theorem and extreme value theorem. So let's talk about the intermediate value theorem and what it says. And so when I think about the intermediate value theorem, I think about a picture, and here's my picture. Over here I have an A and I have a B. And the idea is I really have 2 points. And so this is height f of A and this is height f of B. And what I'm going to do is I take some value in between f of A and f of B. So let's make it just, I don't care, just make it n. And the idea, you can draw a line here at height n. And the idea is if the function is continuous, then you have to pass this green line. There's no way around it because I can't connect these 2 dots in a continuous motion without actually passing it at some point in time. So here I go, I pass the line. And so what happens then is that we hit this existence of the point C as a property that f of C is equal to the height of n. That's it. So the statement, how we write this out, it's basically we say if n is an element of R, let's do it like this. If n is an element of R, that is between f of a and f of b, then there exists a c between a and b such that f of c is equal to n. So that's how we write it out. But hopefully the picture is rather obvious. If a function's continuous, you cannot connect these 2 points without passing that horizontal line, the green line. All right, let's look at the extreme value theorem. So the EVT, the extreme value theorem. All right, this theorem basically says that the absolute minimum and the absolute maximum are obtained on the interval AB. So the absolute, let's use the word global because we're using global. So the global, absolute's the same thing. Right? The global minimum and maximum are obtained on the closed interval AB. So really, if you want to draw a picture of this, the idea is you have your A, you have your B, and I don't know what my function looks like, but whatever it looks like, it may go up, it may come down, it may go up again. But on a closed interval, you're guaranteed to reach your, in this case, this would be the global maximum. So my global max. And also, you'll reach your global minimum, which is down here. So this is my global min. It's the very highest point on the graph or the very lowest, so my global min. And so the extreme value theorem guarantees that this will occur on a closed interval. If the interval is not closed, it may not obtain its global maximum or global minimum. I mean, you could just think of the graph from minus infinity to infinity of x squared. It does not obtain a global maximum from if you're going from minus infinity to infinity, if you take in all possible inputs, because it's continuously going up on both sides. It does obtain its global minimum right here at 0, but it doesn't obtain its global maximum. And you can come up with other examples that you can restrict the domain or your input from -1 to 2. So we can do an example like that. Let's just do one real fast. So like suppose, what did I say, -1 to 2. So let's do an open interval, -1, and let's close it off here, 2. And I can draw a graph that has a global maximum, but doesn't obtain it because there's an open circle there. So let's just draw a line, and I can do a closed circle. Actually, let's do an open circle down there too. So it doesn't obtain its global min or its global max on this half open interval. Right? So the global maximum, of course, would be height. Let's say this is height 3, height 2, height 1. So the global maximum would be height 3, but it doesn't obtain it. And the global minimum would be height 1, but it doesn't obtain it on this half open interval. We could even confuse it a little bit more and not make it continuous, and then you definitely don't obtain the global min or global max. So there are all kinds of things that you can do, but as long as your function is continuous and you're on a closed interval, it will obtain the global maximum and global minimum. That's what the extreme value theorem says. And then finally, the hardest one, I think, for us to kind of understand at first is this mean value theorem. So the mean value theorem, because it uses the fact that f needs to be differentiable on the interval AB. So if f is differentiable, which means the derivative exists on AB, then so let's draw the picture. So over here, here's the picture I have in mind. I have my A, I have my B, And basically, it's like you have these 2 points again, sort of like the intermediate value theorem. So here's my f of a, and here's my f of b. And who knows what the graph looks like, so I'm just going to draw a kind of nice graph here, connecting these 2 points. So that's my f of x. And so what this one says is basically if you connect these 2 points here, these 2 dots, so let's connect them with a nice line. The slope of that line is going to be given by the rate of change, the average rate of change between these 2 points. So I have a and f of a, and b and f of b. So I just take the average rate of change, which is really just a slope of that line. So if you take f of b minus f of a, and you divide it by b minus a, the mean value theorem just says there is some point on the function that has that same rate of change. So some point along here, let's try to find it, maybe right about here. And you can draw it then. You're going to have a tangent line which is parallel to that green line. So my tangent line here is going to be parallel to the green line, and that's going to give me this point C. So this rate of change, the slope of the green line, is going to equal f prime of c, because f prime of c, remember, is the rate of change, the slope of this red line. And so over here, we can finish off the statement of the mean value theorem. If f is differentiable on the open interval ab, then there exists a c inside that interval ab such that f of b minus f of a divided by b minus a is equal to f prime of c. And we talked about how you can relate this to when you travel a certain distance and you take the average velocity. You know that if your average velocity was 80 miles per hour from point A to point B, let's say, at some point in time you had to be driving 80 miles per hour because velocity is a continuous concept. You can't just jump from 60 miles per hour to 70 miles per hour. You have to go from 60, 61, 62, 63, and every number in between to reach 70.